So in this video, I'm going to take you through frontier molecular orbital theory. And frontier molecular orbital theory, I think this focuses on using the HOMO of one reactant and the LUMO of another reactant, the HOMO of one reactant and the LUMO of another reactant to aid in understanding chemical reactions. Before we be able to describe pericyclic reactions, we have to know the molecular orbital theory, what the molecular orbital theory is. So this is what we are going to use. Basically, we are going to apply this principle in predicting the reactivity of molecules. So now, for us to understand everything easily, we have to know what molecular theory is and what HOMO LUMO represents. I think understanding this basically will aid us to get to know what is left. So let me take you through these three things. So let's continue. I'm going to start with the molecular orbital theory. I have a video on how to draw the molecular orbitals of heteronuclear atoms and then diatomic molecules too. But for us to understand this video very easily, so let's revise. Let's make a short revision on that. So the molecular orbital theory is basically, let's say if we have H2, we know that this hydrogen is a molecule, right? It means we have two hydrogen atoms coming together to form this H2, right? So now, for us to draw the molecular orbital of this hydrogen, this diatomic molecule, let's call it a hydrogen molecule. So we know that hydrogen has only one electron in its orbital. Let's say we have one s orbital, but this is the case that we have two hydrogens coming together to form a hydrogen molecule, right? So now the one electron at the end of the day, that means this hydrogen brought one electron from its 1s orbital, and this one also brought one from its 1s orbital. So at the end of the day, if we are to draw the molecular orbital diagram for this, what we have to know is that according to the molecular orbital theory, it said that molecular orbitals are formed by linear overlap of two atomic orbitals or more. So this hydrogen and this hydrogen, let's say we have a hydrogen here and one hydrogen here. We have one s hydrogen here and this one s hydrogen. This is for this hydrogen. Let's say this is one of the hydrogen and this side is for one of the hydrogen. They are coming together. The two atomic orbitals, when they come together, they form two molecular orbitals too. When two atomic orbitals come together, they form two molecular orbitals. That is the bonding and the anti-bonding, right? So bonding, let's say sigma 1s and the sigma asterisk 1s. So now each of the hydrogen brought one electron, right? So in this case, this is the individual atomic orbital. So one s here, one s here. What we are going to focus on is the molecular orbital. What is in the middle? So we are going to take this one as, because this is what we need. So at the end of the day, this hydrogen brought one electron. This one also brought one electron. So we are going to have two electrons. In filling the molecular orbital, one of them has to be filled first before we go to the other one, right? So now that you understand what molecular orbital is, it means that we have atoms, either two or more, coming together to form a bond, and in their molecular orbitals. This is what we are much concerned with. So this atom come together to form a molecule, and we are taking their molecular orbital into consideration. So now let's go. Let's look at what the HOMO and LUMO means. So assuming we have a molecular orbital like this, let's say we have a certain molecule formed, and this is the molecular orbital that we got. We have electrons in the orbitals. Now, let's say this is where our molecular orbital, the available electron, this is where we can fill up to. So this means this is the end of our electrons. As the molecule, when the molecule was formed, this is how the molecular orbital looks like. So we are going to identify the HOMO and the LUMO. And the HOMO means the highest occupied molecular orbital. Like you know already, we are talking about molecular orbital. So which of the molecular orbital here is very high in energy? Looking at our energy diagram, as we go up, energy increases. So this is our highest occupied molecular orbital. Highest occupied molecular orbital, which is the HOMO, right? So after this, next to this is going to be our LUMO, the lowest unoccupied molecular orbital. Why? Why are we calling this the lowest? So we can see that from the molecular orbitals, these are the only orbitals that are not full. So which of these is very low in energy? So it's definitely this, because as we go up, as our energy, indicated it that as like it is indicated by energy diagram, as we go up, energy increases. So this is the lowest unoccupied molecular orbital. So the reason why frontier is much concerned with the LUMO and the HOMO is that if there should be an excitation, electrons are easily going to be removed here to this place, right? Very hard for electrons to move here to that place. So that is why the LUMO and the HOMO are very much concerned. We are concerned about them in this theory. So the HOMO determines the nucleophilicity or basicity. So this is exactly where this is the orbital through which the molecule donate electrons, right? So and this one, as this one is determines nucleophilicity, this one also determines electrophilicity, where the molecule can accept electron, right? So this place and this place. So let's continue. I definitely going to make this. I'm going to make this video like this for you to get the understanding from side. Some most of the time, if we start without looking at the molecular orbital, knowing the HOMO and the LUMO, understanding is sometimes going to be difficult. So let's focus on this very well. So and the HOMO and the LUMO are the frontiers here. The frontiers here. So just know that. So when we are going to predict the reactivity of a molecule, a given molecule, we are going to use frontier analysis. So in the frontier analysis is basically we are taking the LUMO and the HOMO into consideration to predict the reactivity of the molecule. And we are going there. We are going to know everything today as much as possible. So now that we know HOMO and LUMO, let's proceed. So one thing you also need to know is that we are going to be dealing with conjugated system. So conjugated system in a sense that we are going to be dealing with double bond, molecules, which are alkenes, right? Something like this. So we are going to be dealing with things like this. So conjugated alkene, because the double, we have two double bonds which differ by only a sigma bond, right? So anytime you see something like this, you can say this one is a conjugated alkene, right? So this is a conjugated alkene because why? The two double bonds differ by a sigma bond. I thought of this. Maybe you might be wondering why LUMO? Why lowest unoccupied? Because you could see that these are the unoccupied molecular orbital, right? So here electrons are filled here. We have this molecular orbital filled with electrons, but these orbitals are not filled with electrons, right? So they are unoccupied by electrons. And we know that the Lewis dot structure is the best to visualize molecules, but this is not the great option for electron delocalization because we are always dealing with single and double bonds and things like that in Lewis dot structure. So the theory that is going to help us know to analyze our delocalized electron is going to be the molecular orbital theorem. And this molecular orbital theorem, one thing you have to also know is that we are going to be dealing with the p orbitals. I said that again. Let me say that again. P orbitals, because the molecular orbital theory is going to help us view molecule very well into details as compared to the Lewis dot structure. Let me take you back to this again. As we were talking about molecular orbital, we made mention of molecular orbital. We have bonding orbital and then anti-bonding orbital. And you can see that these anti-bonding orbitals and then bonding orbitals are formed by certain phenomenon. The constructive and destructive interference, right? Constructive and destructive overlap of the p orbitals. So we all know that the p orbitals has two lobes and I mean two lobes with opposite phases, often depicted as shaded or unshaded, and sometimes plus or minus. So this is how a p orbital looks like. This something like this. So let's say um, these are the phases of our two orbitals. P orbitals. So in a case that we have these two phases closer to each other like this, so this is going to be a constructive interference because these two orbitals are in phase. Are in phase because looking at the shaded portion, they are, up, not in the opposite manner. So we can also have something like this where the shaded portion is up and for this the shaded portion is down. So in this case, this is going to be destructive, destructive overlap. So this is going to give us anti-bonding molecular orbital, and this is going to give us a bonding molecular orbital. So now that we know the p orbital has two phases, there can be a case where the phases will be, where the two p orbitals or the p orbitals will be in phase or they are out of phase. So be in phase, out of phase. So that is to say, if we have, let's say, two p orbitals here, these two orbitals can come together to form, to be in phase, where the phases, they will be in phase, and there can also be a case where we are going to get them to be out of phase, right? Out of phase means the shaded portions are in the opposite manner. So in this case, we are going to get, you see, these are in phase, so this is going to be a bonding orbital, right? And these are not in phase, so they are anti-bonding orbital. So it's not always that we get two orbitals, right? We can also get three orbitals where they can all be in phase depending on the molecule that we are analyzing. And we can also have something like this where they are not in phase. This way, out of phase. So now that we understand what LUMO and HOMO is and what the molecular theory is about, and you understand that the p orbital have two phases, and there can be a time where the phases will be in phase or out of phase, right? So now let's apply this by trying to analyze a molecule. We are going to use it to draw molecular orbitals of a given molecules, right? Conjugated system specifically. Now we are going to analyze electron delocalized system. So now, assuming we have a molecule like this, yes, like this. This is 1, 2, 3, 4. So 1,3-butadiene. So let me name it here. 1,3. Sorry, come on. 1,3-butadiene. So we are going to draw the molecular orbital for this molecule, the molecular orbital diagram for this molecule. So what you have to do is that, how are you going to draw the molecular orbital diagram? What you have to do is that, analyze your molecule very well. Me, I prefer drawing the molecule again. This is the molecule, right? So we have a double bond here and a double bond here. So now what you have to do is just indicate your p orbitals like this, like that. I'm just drawing it anyhow. I know you can draw better. So when you are done, forget about the hydrogens attached to the system. So we are looking at p orbitals, right? Let's look at the number of carbon atoms that we have. So you can name them. Let's say we have 1, 2, 3, 4 carbons, right? So we have 4 atoms, right? 4 atoms, right? So 4 atoms. How many electrons we have? In detecting your electrons, just look at where the double bonds are. So double bond, we have one electron here, one electron here, one electron here. So at the end of the day, we have 4 electrons. If it happens that we had another double bond, we are going to take 2 electrons from there. So 4 atoms, 4 electrons, right? So now we know 4 atoms, 4 electrons. So what are we going to get for um, our molecular orbital? I mean, what possible molecular orbital can we get here? So four atom, 4 electrons, same 4 possibility of we having MO, molecular orbital. So now that we are done analyzing the molecule like this, then everything becomes easier. So mind you, we have 4 atoms and 4 molecular orbital. So you can now go ahead, indicate your energy diagram. This is your energy. So how many orbitals we have? 4, right? So 1, 2, 3, and then 4, right? So now, how many atoms do we have? 4, right? Carbon 1, 2, 3, 4. So let's draw our carbons on this. So I'm going to do that. 1, 2, 3, 4, right? So here 1, 2, 3, 4, right? Not drawn to scale. I know you can do better. So 1, 2, 3, 4. After this video and you don't understand this, let me know so that I'll get you a boiled egg. So 1, 2, 3, and then 4. So 4 atoms, 4 possible molecular orbitals. So 6 atom, 6 possible molecular orbitals. So this is how we are going to do it. When we are done, let's do something like this. I'll tell you what this is. This is where our electrons will come and sit. So let's name this MO1, molecular orbital diagram 2, molecular orbital diagram 3, molecular orbital diagram 4. This is part 1. After you are done drawing your molecular orbital diagram like this, I mean setting up the layout for the molecular orbital diagram, then now one thing we have to take note is nodes. Nodes. So what exactly are nodes? If we have 2 orbitals that are not in phase, that are out of phase, we are going to get a node between them, right? So this node, so if they are, I mean, in phase, then there's no node between them, right? So just know this. And the most stable conformation is going to have 0 node, right? Just know that. So let's start number our molecular orbital from 0 to where we have to end. 2, 3, 4. Is it actually 4? 0, 1, 2, 3. Yes, I should be getting 3. So now this means in first molecular orbital we have to get 0 node. There's no node between them. The individual atomic orbitals. And here we have to get 1 node, here 2 nodes, here 3 nodes. Let's see how we can do that. So we know the most stable conformation is those who have, those who have 0 node, right? So all these are in phase. Phase. When we are done, we are going to interpret what this actually means. So after that, we are going to have 1 node here. So let's divide that orbital into 2. So 1 node. The node 2, you can also decide to bring a dot, but I prefer dividing this way. So this means these orbitals are going to be in phase and these one are going to be in phase. There's a node separating them. So this means, let's say we can have orbital like this one being in phase and these two also being in phase. Sorry, this supposed not to be upwards, right? Sorry, have to shade this downwards. It has to be the opposite of what is here. So sorry for this. I don't know how to correct this mistake. So let me use so these are in phase and these are also in phase. So up, down here. So now that we are done with this, we have to get 2 nodes here. So how do we get that? So remember, here we have no node. We have no node, right? And here we have 1 node in the middle. This is my trick of doing it. As far as we have 1 node in the middle, let's move the node to the left a bit. I mean, we need two nodes, right? To the left. So we are going to get a node here, and let's do the same to the other side. So now we have two nodes here. This means, you see, those which are not divided by nodes will definitely be in phase with each other. So this one, let's say if this is upward, we are going to have these two atomic orbitals to be in phase, right? Possibility. So after that, we are also going to get this one like this, standing alone. So let's deal with this, the MO4. Here, we already, as I told you that, we already are, like I already told you that this is one trick of moving the node. So this, now the node is here, and the other one is here. We are going to get three nodes, right? So we're just simply dividing the whole molecule. So after the node is here, you decide adding one. But I don't want to make this confusing to you. This one is just simple. But when we have a molecular orbital that is huge, sometimes indicating the nodes becomes something difficult. So, but you don't worry. So now we are going to get all of this not be in phase, like this, like that. Now that we are done indicating our phases, so let's look at our electrons. First of all, we already took care of this and that. Our electrons are coming to sit here. How many electrons we have? Four, right? So 1, 2, 3, 4. Don't forget to fold single first before, I mean, to fold each orbital completely before going to the other one, the next one. So now we have our electrons here. So our last electrons in this orbital. Where can we, which of these orbital is our HOMO and which of these orbital is our LUMO? You will see that this is our highest occupied molecular orbital. So definitely this is going to be our HOMO, and next to that will be our LUMO, right? This is our lowest unoccupied molecular orbital. Energy diagram indicates that going up, energy increases, right? So we have this orbital unoccupied, this one unoccupied, but this is the lowest, so LUMO. And there is an energy gap between the HOMO and the LUMO, right? And this energy gap is also responsible for colors in some conjugation systems, right? So that is one of the benefits of this energy gap, or core effects of this energy gap. So now, what does this actually mean? What How can this thing make sense to us? So you could see that for the Lewis structure, we have the molecule only like this, right? So this one is not going to tell us which orbitals are the electron delocalized on those stuffs. But this right here is going to tell us that. You could see that we have all these. I mean, the first MO1, we have MO1, all of the atomic orbitals, they are in phase, right? This means that all of the atomic orbitals are sharing two electrons. I mean, two electrons are delocalized between all the orbitals. So in molecular orbital 1, let's try to, if this is our alkane, according to our molecular orbital, from MO1, according to our molecular orbital diagram from MO1, we have two electrons delocalized throughout the four carbons. Mind you, this indicate carbon 1, carbon 2, carbon 3, carbon 4, right? 1, 2, 3, 4. So in MO2, what is happening here? We have two of the orbitals being in phase. We have two of them here being in phase, and these also being in phase. So this is to tell us that we have carbon 1 and carbon 2 being in phase, indicating that carbon 1 and carbon 2, there's two electrons delocalized between them, right? So carbon 1 and 2, we also have a delocalized electrons here, and carbon 3 and 4, we also have delocalized electron there, 3 and 4 delocalized, right? So let's look at our MO3. Our MO3, you could see that we only have carbon 2 and 3 being in phase, right? So 2 and 3. So that means we have only two electrons that are delocalized between carbon 2 and 3, right? So let's continue. And for our last MO, our last molecular orbital, which is MO4, you will see that none of the atomic orbitals are in phase, right? Good. Later on, we are going to apply this principle in predicting the reactivity of pericyclic molecules. So just master this. So you have to know this. From carbon 1 to 4, we have 2 electrons localized between those. And from 1 to 2, we also have 2 electrons there. That is 1 to 2. We have 2 electrons delocalized there. And then 3 to 4, and we also have 4 to, 2 to 3, and we also have 3 to 4. So just know that. In phase means we have 2 electrons that are localized between them. So let's look at another practical example. So I already have the molecular part of the molecular orbital drawn. So this is the molecule that we are going to deal with. Let's name it. It's very important, or something, or I don't know, but I just feel like naming it 1, 2, 3, 4, 5, 6. So we are going to get 1, 3, 1, 3 hexa triene, right? Triene, because we have 2 and 3 double bonds. So looking at this molecular orbital, let me take you how I got this. So let's analyze our molecule. We see our molecule. Let's start naming the carbons in it. Like I said earlier, 3, 4, 5, 6. We have 6 carbons, right? That means we have 6 atoms, right? So 6 atoms, and how many electrons we have, and how many molecular orbitals are going to be possible. We have 6 atoms. Let's count our number of electrons involved. So we have 1, 2, 3, 4, 5, 6. 6 electrons also involved. This is somehow easy to predict, right? And now we are going to look at our possible molecular orbitals. We are also going to get 6 possible molecular orbitals, right? Orbitals. So that is why I already drew this. So you can see that we have 1, 2, 3, 4, 5. Oh, this is actually 5. 1, 2, 3, 4, 5. Oh, I have to add 1. So I'm done adding it. So that is at the top right here. So I have 6 atoms, right? So 6 atoms. If you look at this very well, 1, 2, 3, 4, 5, 6. You can see that 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Everything has. All the molecular orbital, they have 6 atoms. I don't know whether you get this. It means that each molecular orbital has 6 atoms, right? Okay. So I think this is okay. Let's start indicating our nodes. We know firstly we are going to start from 0, 1, 2, 3, 4, right? So the first place will have 0 node, which means 0 node means all of them are in phase, just like that. So now the second one, we are going to have 1 node. So what you have to do is just divide the molecular orbital into 2. Then you are going to get something like this. 1 node means immediately after the node, you could see that this one, those are the individual sizes will have the same, will be in phase, right? Will be in phase. So let's look at this. You see these are in phase. The problem comes in when we have a node. So this one are also going to be like this. Okay. So now when we are done with that, what we have to, we also have to look at the second one, which will having 2 nodes. This is where my tricks come in. Like I told you earlier, you could see that this one we have the node in the middle. So decide to move the node to the left a bit. So 1 by 1. So let's bring in the node here, and you do the same to the other side. So 2. If you master this, no matter how huge the molecular orbital is, you are going to find your way out. So this one will be in phase, and this one will also be in phase. This right here also be in phase, right? So now we are done with this. We have to get 2 nodes here, and this one we have to get 3 nodes here. So let's do that. So my trick again, as far as we are here, let's move 1 to the left, right? So 1, and also do the same to the other side. And when we are done, what we can also go ahead and divide what is in the middle of the two, because we have to get three nodes, right? So let's start shading. This right here is there. This one are in phase. This one are also in phase, and this one is also right here. I hope you are actually getting this. So now that we are here, then ask me, now that we are here, what are we going to do again? Like I told you, like continue moving to the left. And now that we are here, what should we do? We just have to come there, and then like the other one, you come here, then add one again. So when you're up to the end, just start going inside again, okay? So you were here, right? You were here from your right, so you're here already. So add one page. So you were here, and what are we going to do here? We need four nodes, right? Huh. So what are we going to do? So you also do the same. Yeah. When you were here, when you were at MO4, you moved to this side, and you also moved to that side. When you're done, you divide the molecule into two, the orbitals into two. And now you are here, you just stay there and go forward one, and here to also stay there and go forward one, right? So let's start shading. So we are going to get this one to be like this, and this one to be like that. And this one, no separating them, so they have to be in phase, right? So they have to be in phase. So, and this one too, there's a node between them, so you have to get opposite. You have to be in opposite phase, right? So that's it for that. We are left with MO6. So MO6, we have to get 6 nodes, right? So look at this: 1, 2, 3, 4, 5. Not 6. This will be 5. Yes, because when we started numbering our node, we started from 0, 1, 2, 3, 4, 5. So this will actually be 5, right? So we have to get 5 nodes here. So 1, 2, 3, 4, 5. You will see that at the end of the day, the last molecule, they are all going to end up not being in phase. In most cases, like as the beginning start, and we have all the orbitals which are in phase, right? So at the beginning, we have all the orbitals which are in phase, and lastly, we definitely going to have the orbitals in the molecular orbitals not be in phase. So that's way and that way. So I hope this makes sense. This is okay, right? This is the molecule that we are drawing, its molecular orbital diagram. So now that we are done, we already knew that 6 electrons were involved. So let's start filling up. So 6 electrons, we are going to get 1, 2, 3, 4, 5, 6, right? So the end, after this, we are going to identify our HOMO and the LUMO, right? Our HOMO and the LUMO. So you will see that this is our highest occupied molecular orbital. So HOMO, and next to that is going to be our LUMO. LUMO, energy gap. Now that we are done drawing our molecular orbital, in this video, I'm actually not going to tackle the feasibility of the reaction. I'll tackle that in another video. Like we are going to tackle the cycloaddition reaction, the 3 types of pericyclic reaction too. So you can check that out. So looking at this, our Lewis structure is just this, right? So look at what we got from our molecular orbital. Let's start analyzing that. Okay. Oh, the same molecule. So no. So this is a normal Lewis dot structure. So just like this. So let's analyze this from the result that we got from a molecular orbital diagram. Just using the results that we have from our molecular orbital diagram. So now this one is cancelled. So looking at MO1 first molecular orbital, you will see that all the orbitals are in phase, right? So that means we have two electrons that is delocalized throughout carbon 1 to carbon 6. Carbon 1 to carbon 6. So this is to tell us that from carbon 1 to carbon 6, we have two electrons delocalized throughout the system, right? Wave function. And let's see what is happening in MO2. You will see that carbon 1, 2, 3 are all in phase. So two electrons delocalized between them, and 4, 5, 6 also the same. So 1, 2, 3, 4, 5, 6. We'll see that. So this is just a basic idea behind this. So from MO3, you could see that we have two electron delocalized between carbon 5 and 6, and then 1 and 2, and 3 and 4. And here too, you could see that we have delocalized electrons between 2 and 3, and then 4 and 5, right? So here we only have 3 and 4 delocal that it's only 3 and 4 that we have delocalized electron between them, right? So this is basically what is behind the frontier molecular orbital theory. So now in next video, we are going to apply it in predicting the reactivity of pericyclic compounds, because we know that molecular orbitals are formed by linear combinations of atomic orbitals, and the phases of the atomic orbitals determines the phases of the molecular orbital. That is why the frontier theory is about. So this molecular orbital was formed by linear combination of atomic orbitals, each individual atomic orbitals coming together from the molecular orbitals. So the phases of the orbitals that we have in the molecule is going to tell us the phases of the atomic orbitals going to determine what the molecular orbitals, and we are going to use this to determine whether a reaction is going to happen or not. To detect possible reactions in pericyclic compounds. That is for our next video. So if you have any problem, you can comment below, and let's see how best we can handle that. Don't forget to support this channel by liking and subscribing. Thank you for watching.